it is a container for homogeneous data. That is, all the elements of the ND array must be of the same type. Compare that with the lists of Python. A list can contain heterogeneous data elements, whereas ND array, NumPy array, has to be a homogeneous collection of elements. And every array has a shape. A shape is basically a tuple indicating the size of each dimension, and D type, an object that describes the data type of the array. Okay. So every ND array has two important attributes. One is the shape, which is the size of each dimension. Okay. And second attribute is D type, which describes the data type of the array, or data type of the elements contained in the array. You can create a one-dimensional array, which basically is a vector. Okay. So the shape of the array is a tuple 4. Okay. You can also create a two-dimensional array. Okay. Shape in this case is 2, 3. That is, it has 2 rows and 3 columns. And you can also create a three-dimensional array where the shape is 4 rows. Associated with each row, you have 3 columns, and associated with 3 columns, you again have a third dimension containing 2 elements each. In fact, you can create more than 3-dimensional arrays also using NumPy. Okay. So shape of this is 4, shape of this is 2 by 3, shape of that is 4 by 3 by 2. This is a vector, this is a 2-dimensional array, and that is a 3-dimensional array. How do we create these arrays will become clear shortly. Okay. I made a statement that NumPy arrays are faster than Python lists. Why is that so? NumPy arrays are faster than Python lists because NumPy uses fixed type. That is, all the elements must be of same type. And more importantly, the size of a NumPy array is much lesser than size of a Python list. Okay. This demonstrates if the list contains an item or element 5, okay, the binary representation of 5 is this, okay, or rather this 101, and in the Python each element organizes as size, which is of 4 bytes, reference count of 8 bytes, object type of 8 bytes, and object value, that is essentially 5, is again of 8 bytes. So that makes it 28 bytes. 28 bytes represent an element on the list, whereas compare that with NumPy arrays, it just requires 4 bytes to represent the binary representation of this array element 5. Okay. So what this indicates is the size of a Python array is much smaller than size of a Python NumPy array is much smaller than size of a Python list. And what does that lead to? That leads to faster iteration through the array over iterating through the list elements. NumPy arrays are allocated contiguous memory. That's another point that makes NumPy arrays faster, whereas lists are allocated memory that is non-contiguous. Okay. That is, you get a sequence of one block of memory for NumPy arrays, whereas you could have a block of memory allocated at different locations on the memory for a Python list. Python lists are resizable and can contain elements of different types, whereas NumPy arrays have fixed size at creation. Okay. Does that mean I cannot increase the size of a NumPy array? You can always increase the size of a NumPy array by creating a new array by adding the extra elements. So NumPy arrays have fixed size at creation and contain a fixed type of data. And this in fact leads to this point, that is, no type checking is required while iterating through NumPy arrays, because the data type is fixed and the memory is contiguous. So iterating through the NumPy arrays is faster than iterating through Python lists. Okay. Take a look at this small piece of code that I will be executing. This will show you how fast the NumPy arrays are. Okay. Now I have imported module time to record the current time and I also imported NumPy as an alias NP, and I will create two lists of 1 million elements. 1 million elements. Okay. All the two lists will be populated with 0 to 9,99,999, and A1 and A2 are two NumPy arrays, that is a range size, that is it will also create the same array ranging from 0 to 1 million minus 1, that is 0 to 9,99,999. So these two are two NumPy arrays containing 1 million elements, and these two are Python lists containing 1 million elements. Okay. I will note down the starting time, and then I'll add the two lists. Okay. Zip gives me an iterative object which will pick one element from each, and those two elements are added up and are appended to a new list. So I will perform the addition of the two lists, and I will record the current time minus the time when it was started in 2000. That gives me the number of seconds, okay, elapsed for performing the list addition. And I will again start the time and then add the two arrays. Look at the simple way, that is you can directly use addition operator to add two arrays of 1 million elements. And that creates a new array, and I will record the time minus the starting time in 2000 gives me the time elapsed in terms of seconds to perform array addition. Okay. Let us look at the execution of this program. Okay. The same program is here. Okay. It says time required for list addition is 296 milliseconds, whereas array addition took hardly anything. Okay. It is not even in terms of milliseconds. Okay. That goes on to show how fast NumPy arrays are compared to lists. NumPy allows a lot of more operations apart from the basic insertion, deletion, append, or concatenation operations. Okay. Look at this. A and B are the two arrays or two Python lists. Okay. A equal to 1, 2, 3, and B equals to 4, 5, 6. A is a list, and B, A is a list and B is another list. When I perform addition, it gives me A and B concatenated together. But can I perform multiplication on two lists? No, it shows me an exception. Type error, cannot multiply sequence by non-int type list. Whereas, let me create a NumPy array. Before you can use NumPy array, you need to import NumPy. Okay, I will import it as an alias NP, and then I'll create np.array. Array is a constructor that takes in an object, that is sequence of elements, D type. Okay, that is the data type associated with the elements. Okay, I simply create an array here, and I will create another array containing 4, 5, 6 as the elements. A plus B, okay, interestingly, will not concatenate A with B, but it adds 1 with 4, 2 with 5, and 3 with 6, and returns me the list as 5, 7, 9. Okay. By now you must have already guessed what A into B gives me. A into gives me 4, 10, and 18. That is 1 into 4 is 4, 2 into 5 is 10, and 3 into 6 is 18. Okay. So you can simply use the regular operators, mathematical operators like minus or divide to perform the required operation on the entire array. Okay. Look how efficient it could be to use NumPy arrays over Python lists. Okay. So this definitely is an error in Python list, whereas A into B on two NumPy arrays gives me the multiplication performed on individual elements of the array. how do we create NumPy arrays? Okay, there are different ways in which we can create NumPy arrays. We'll look at a few of them. The first one is we already have seen, to use the function or method array on NumPy. That is, array object d type equal to none. Okay, by default d type will be int 32. That is, it will be 32 bits associated with each element, or 4 bytes with each element. Okay, so np.array will create a vector. Okay, for example, a equals np.array 1 2 3 4 5 will create a NumPy array having those elements. Okay, and what is d type? D type is the data type associated with the individual elements. I did not specify the data type here. If I just look at the attribute d type, it shows me int 32. That is, by default each element is consuming 4 bytes of memory. Okay, but wasting 4 bytes of memory for elements such as 1 2 3 4 5, which hardly consume less than 32 bits, we can always specify the d type as what? Okay, let us say 1 2 3 4 5, the same array. Give the second parameter d type equals int 16. Okay, this will create the same array. Okay, but its data type is now 16. That is, it consumes 8 or 2 bytes for individual element. Okay, that saves memory. Okay, whereas earlier one was consuming 32 bits, that is 4 bytes, whereas now the array elements require just 16 bits. Similarly, you can create a 2-dimensional array as this. Okay, that is, b equal to this. Okay, b will now be a 2-dimensional array. Okay, having 3 rows, 1 2 3, 3 rows, and in each row 3 elements. That is, it will be a 3 by 3 matrix. What will be the data type of individual elements? By default, it will be 4 bytes. You can use another method called arange to create a NumPy array. Okay, its syntax is NumPy.arange starting value, end value, step value, and d type. If you don't specify, it will by default be int 32. Okay, so np.arange, I have used np as an alias for NumPy. np.arange 10 creates a vector from 0 to 9. That is, if you don't specify start, it will start from 0 and stop at stop value -1. That is 0 to stop -1. Okay. Okay. C will be an array with the elements from 0 to 9. Arange can also be used as np.arange start value, stop value. In this case, C will be an array having the elements starting from 1 up to but not including 10. So it will be an array of 9 elements, 1 to 10. If you want to create an array of elements 1 to 10, then you probably have to say this. That is np.arange 1, 11. So it is up to but not including. So if you want to generate an array from 1 to 10, then you have to specify the stop value as 11. This will create an array from 1 to 10. Okay. And of course, the type of elements will be int 32. but you can always specify the D type as int 16. This will create array with the type as 16, or you can specify int 64. This will create the array with elements, each element consuming 8 bytes. And of course, you can also specify the step value. That is, if you say 1, 10 in terms of 2 steps of 2, then it will create 1, 3, 5, 7, 9. Okay, that is, start from 1, step by 2, and range up to 11 minus 1. So 1, 3, 5, 7, and 9. Okay, so these are the two ways in which you can create a NumPy array. There are other ways also. As we progress along, you will understand the other ways of creating NumPy arrays. Okay, the first one is the use of the constructor array, and the second one is to use the method arrange. Okay, let us look at some of the important attributes of NumPy arrays. Okay, we have seen one attribute already. Okay, what do you think it is? It is D type. The D type which describes the data type of the elements of the array. Look at the other attributes that are of relevant to us. The first one is dimension. Okay, that is ndim. Ndim represents the number of dimensions or axes of the array. That is A. Okay, we had created an array A. Okay, as this A equal to np dot array 1, 2, 3. Okay, A dot ndim gives me 1. That is, it's a vector. Okay, whereas if I create an array of 2 dimensions, 1, 2, 3, 4, 5, 6, 7, 8, 9. B is a 2-dimensional array. B dot ndim returns me 2. Okay, because B is a 2-dimensional array, whereas A is a single-dimensional array, or it's a vector. B is a matrix, whereas A is a vector. So this is the first attribute of NumPy arrays, that is ndim. Okay. Second attribute is shape. ndarray dot shape. Shape is a tuple of integers representing the size of each of the ND array in each dimension. Okay. The array A that we just created is a vector, so it's a tuple indicating the shape as 3, whereas B's shape is, it's a 3 by 3 matrix. Okay, it's a 2-dimensional array, and the shape of array is 3 by 3. Okay, that is, we have created A, and shape of A will be 3, whereas the shape of B will be 3 by 3, because it's a 3 by 3 matrix. Okay. The third attribute is type. Okay. This we have already seen. ndarray.dtype. Dtype tells the data type of the elements of a NumPy array. And in NumPy array, all the elements have to be of the same data type, essentially because NumPy arrays are same as C-style arrays. Okay. So the array that we just created, its D type is int32, because we did not specify, while creating the array, we did not specify the D type. So by default, the D type of A will be int32. Similarly, we did not specify any data type for B, so the D type of B will also be int32. Whereas if I say D equals np dot array 1, 2, 3, D type as int16, then the D type of D will obviously be int16, that is 2 bytes for each element. So these are 3 attributes, that is ndim, shape, and d type. First one gives me the dimension, second one gives me the shape in each dimension, and the d type gives me the data type of each element of the array. The other attributes are size. Okay, size is the total number of elements in the ND array. It is equal to the product of the elements of its shape, obviously. Okay, the shape of A is 3, and 3 into 1 will be size. That is, A dot size will be 3, whereas B dot size will be 9, because shape of B is 3 by 3, and obviously it contains 9 elements. So size of B is 9, whereas size of A is 3. The next one is item size. Item size returns the size in bytes of each element in a NumPy array. Okay, that is, A dot item size is 4. Why 4? Okay, what item size must be now? It is 4, because d type is int 32, whereas d dot item size gives me 2, because the d type of d is 16. How about item size of array B, elements of array B? It again will be 4, because d type of B is 32. So each element requires 4 bytes. If I create another array E, np dot array 1 2 3 4 5, d type equals int 64, then E dot item size will be 8. Let us create another array with 1 2 3 4, and d type equals float. Then F will be a floating point array, 1.0, 2.0, 3.0, and 4.0, and F's d type will obviously be float 64, because I specified the d type to be float. So d type of F will be float 64. And what do you think the item size of F will be? It obviously will be 8, because the size of each element, if you represent that as float, will be 8 bytes. Okay. So item size property or attribute returns the size in bytes of each element of the NumPy array. The next dimension, the next attribute is how do we get the total size? Okay, total size, you must have realized by now, is the multiplication of item size into size. What item size gives me? Size of each element on the memory, and size gives me the number of elements. So number of elements into memory consumed by each element gives me the total size occupied by the NumPy array. Okay, so A is this, the d type size is 3, that is, it contains 3 elements, and each element is of 4 bytes. So A dot item size into A dot size gives me the number of bytes consumed on the memory by array A. This can also be done using A dot another property called n bytes. N bytes is same as this. Item size into size is available as another attribute called n bytes. So A dot n bytes will also return me 12. So n bytes is same as item size into size. Okay, these are the different attributes okay, of NumPy array. That is, we have seen ndim, shape, dtype, size, item size, and n bytes. Okay, we'll look at the other aspects of NumPy arrays now. Okay, now we have created a NumPy array. How do we access specific elements? How do we change a value? How do we access a row? How do we access a column? Okay. To access a specific element, you have to specify the row and column indices. Okay. That is R, C. Row index starts from 0 and column index also starts from 0. That was the regular feature for lists. First element of a list is available or accessible at subscript 0. Same is the case with tuples or dictionaries, and same is the case with other languages like C, C++, or Java. That is, each element of the array is accessible via an index that starts from 0 to size -1 for a vector, 0 to row size -1, and 0 to column size -1 for two-dimensional arrays or matrices. Okay. So let us create this array first. Okay. Okay. A is a two-dimensional array. It has 2 rows and each row has 7 elements. Okay. So what is the shape of A? It is 2 by 7. Okay. Fair enough. Now, how do I access this element? 10. It is available at row 1, or rather row 2, subscript 1. This is row 0 and row 1. That is, row 1 is at subscript 0 and row 2 is at subscript 1. And I want to access this element. Where is it? It's at column 0, 1, 2. So this gives me 10. Okay. Subscript 1 refers to the second row, and subscript 2, that is column index, refers to the third element, with 8 being accessible at subscript 0. That is, A of 1, 0 returns me 8. Okay. So this is how you can access individual elements, okay, of a NumPy array. So A of 1, 5, what does it return? It returns second row and sixth element. Sixth element is 13. Okay. This is same as A of 1, -2. Why -2? Negative indexing. Okay. Python permits negative indexing where the last element is available at subscript -1. First element is available at subscript 0. Last element is available at subscript size -1 or subscript -1. Negative indexing is permitted in Python. So this is at -1 and this is at -2. So A of 1, -2 is same as A of 1, 3. That also returns me 13. That is, A is this. A of 1, 5 gives me 13. A of 1, -2 gives me 13. Okay. A of 0 returns the first row. The entire row is returned to me. That is, A of 0 is the first row. A of 1 is the second row. A of colon, 2. Okay. Colon. If you just specify colon, what does that indicate? For all rows. For all rows. In this case, it's a 2 rows. So for row 1 as well as row 2, get me the third element. So the third element of each row will be 3 and 10. So it returns me 3 and 10. That is, this is A of colon, 2 gives me 3. That is, on the first row, third element at subscript 2 is 3, and on the second row, third element at subscript 2 is 10. So it returns me array, sliced array as 3, 10. How do we get a slice? Okay, slicing is same as that of slicing a string or slicing a list in Python. So you need to specify the starting index, stop index, and step value. Okay. And of course, stop index, if you specify the stop index, it is up to but not including the stop index. Okay. For example, a of 0, 0 means first row 1 colon 6 colon 2, that is start from index 1, range up to but not including 6 in steps of 2 and return me the array. Okay. This returns me 2, 4, 6. Why? On the first row, second element is 2, then step of 2, and then step of 2. So it returns me 4, 6, up to but not including 6. Okay, that is 0, 1, 2, 3, 4, 5. Okay, so this also is returned because fifth index, that is 6 minus 1, is still accessible. And this is same as 0, 1, colon, minus 1, colon, 2. Okay, that is start from the first index, that is the second value, and range up to minus 1, that is range up to the last element in steps of 2. Okay, so this gives me 2, 4, 6, that is 2, 4, and 6, which is same as this, that is all rows. Okay, that is 0, a of 0, 1 colon minus 1 colon 2 returns me the same array. Okay, that is start from 1 and range up to the last value and give me values at steps of 2. So 2, 4, and 6. A of colon. Okay, what does colon by itself indicate? It indicates all rows. Okay, here 0 means first row. So look at the first row only. Whereas if you just say colon, then all rows, on all the rows, return 1 colon 6 colon 2. That is right from second value up to but not including the seventh value in steps of 2. So this was returning me 2, 4, 6, whereas on all the rows, that is on both the rows, means it will return me 9, 11, and 13. So it returns me a two-dimensional array. Okay, this returns me 2, 4, 6, and 9, 11, 13. Okay. How do we, okay, so far we have seen how do we access elements. Okay, accessing the elements is either by specifying the row and column indices or by using slicing start index, stop index, and step index. Now, how do we change values? Okay, remember NumPy arrays are mutable. So you can mutate the elements. Okay, that was not the case with tuples, Python tuples. Okay, but Python lists were again mutable. So this is A. What is A of 0, 0? This is 1. Okay, I want to change it. So it is simply 0, 0 equals 10. A will now be 10 to 3. That is the first value, which was 10, has now been changed to 1, has now been changed to 10. Okay, this is how you can change the values. Okay, so A of 1, 5, that is second row, sixth element, assigned with 20, will change the element 13, which is at second row, sixth column, to 20 from 13. That is A of 1, 5 equals 99. This will change 13 has now been changed to 99. A of colon comma 2, that is colon means both the rows. In this case it's a 2 by 2 array, so on both the rows change the third element to 20. So this will change the third column of each row to 20. Okay, so A of colon comma 2 equals 20. So what will A be now? Look that the third value, 2 means third value on both the rows. So 3 has been changed to 20 and 10 has also been changed to 20. 20 and 20. A is now this. What if I say A colon comma 2 equals 100 comma 200? Okay. This will change on both the rows. The third element of the first row should be changed to 100, and on the second row the third element should be changed to 200. Okay, so what will this do? This will change the third element, which was 20. On the first row it has been changed to 100, and on the second row it has been changed to 200. Okay, look how easy is it to change the values across the matrix or across the two-dimensional array. Okay, this is what we just did. Okay, A of colon comma 2 equal to 10 comma 20 will change the third column of the first row to 10 and third column of the second row to 20. Okay. Now we can also create different types of arrays using NumPy arrays. We have seen two ways in which we can create NumPy arrays. First one is to use the method called array, and the second one was to use the method called arange. Apart from these two, we have other functions or methods such as zeros. Okay, np.zeros 5 returns me a vector containing 5 elements. Okay, A equals np.zeros 5 will create a vector with 5 elements. Each of the element is 0. Okay, and of course the data type of each value by default is float 64. Okay, however, we can always create a NumPy array of all zeros. Okay, with the D type specified as int 16. This will create a vector with 6 zeros. Okay, so this is the third way of creating NumPy arrays, that is an array filled with all zeros. Okay, you can also create a two-dimensional array, np.zeros 4 comma or rather 3 comma 5. This will create a matrix with 3 rows and 5 columns. 3 rows and 5 columns. Each of the element will be initialized with a floating point value 0. Okay, and of course you can specify the D type if you want to save on the memory, or if you want to deal with integer values as this. So this will create a 3 by 5 matrix with all zeros filled. Second is ones, that is np.ones. This will create, okay, np.ones 3 comma 3 will create a 3 by 3 matrix with all ones. Okay, that is A equals np.ones 10 will give me a vector with 10 ones, whereas B equals to np.ones 3 comma 3 will give me a 3 by 3 matrix with all the elements being ones. Okay, we can also create a matrix with some specific number rather than all zeros or all ones. I want to create a matrix with all minus ones. Okay, maybe you are working on a traveling salesperson problem and you want to initialize the distances with -1 initially. Then you can always create an array, okay, with say 9 destinations as np.full 3, 3, -1. That is C equals np.full. I want to create a 3 by 3 matrix with all -1s. So D will be a 3 by 3 matrix with all the elements as -1. Okay. And the fourth way is to create a matrix with the same shape as another but with some specific value. For example, the shape of A is 2 by 2. Okay. Look at this. np.array A equal to np.array. Let us create it first quickly. A is a 2 by 2 matrix and A's shape is 2 by 7. Okay. I want to create a matrix of the same shape as A but with different values filled. Okay. So that can be done using a function called Fulllike. Okay. Fulllike A. Okay. So create a NumPy array which is like A, that is whose shape is same as A but all the elements filled with 99. Okay. So if I say B equals np dot Fulllike A with all the values as 99, this will create a matrix or NumPy array B whose elements will be filled with 99, but of course the shape of B will be same as the shape of A. Okay. So that can be done using method called Fulllike. So Fulllike will create a matrix whose shape is same as A but individual elements being specified as 99. So this is another way of creating NumPy arrays. So you can use the method called array or arrange or zeros or ones or full or Fulllike. These are some of the different ways in which you can create NumPy arrays. Okay, we can also create a matrix of random numbers. Okay, in order to use random numbers, you have to use a module called random. So np.random.rand function gives me random values. Okay, so np.random.rand 4, 2 will return a 4 by 2 matrix with random decimal numbers. Okay, let us quickly look at that. So C will be a 4 by 2 matrix, that is 4 rows and 2 columns in each row, but the values will be random values. Okay, so that is given to me by the method called rand available in module random of np, that is NumPy. Similarly, okay, this created me a matrix with random real values. If you want to create a matrix of random integer values, then you can use a method called randint. Okay. For example, C equals np.random.randint 10. Okay. The first is 10 and size equals 3 by 3. What will this do? This will create me a 3 by 3 matrix with values being randomly chosen in the range 0 to 10 minus 1. That is, its start value is 0, but stop value will be 9, 10 minus 1. So in that range, it has picked random values and has created a matrix a 3 by 3 matrix whose shape is 3, 3. Whereas if I say np dot random dot randint 1, 10, size equals say 4, 5. Okay. What will this create? This will also create a matrix whose dimensions are 4, 5. That is, shape of the matrix is 4, 5. But the values filled will be starting value is as 1 and the ending value will be 9. So in the range 1 to 9, values are randomly picked and a matrix of the order 4 by 5 is created, and that will be the ND array C. Okay. So C is ND array, that is NumPy array of the order 4 by 5, and with the elements being filled with random values in the range 1 to 10, excluding 10, that is 1 to 9 to be precise. And of course you can also specify the data type, okay, comma d type equals to int 16, that will create, okay, d type of A is by default int 32. You can also specify the third parameter or the fourth parameter as d type, specifying the type of each element. Okay, so this obviously returns a 3 by 3 matrix with random integers in the range 1 to 10, 10 not included. Okay. Whereas this will give me a 3 by 3 matrix with elements in the range 0, because we did not specify the start value, we just specified the stop value, whereas here it was start, stop. So stop value is 10, so it will create a 3 by 3 matrix in the range, picking elements in the range 0 to 9, that is 10 excluded. Okay. We can also create an identity matrix. Okay. We have a function or a method called identity in the module NumPy. So np.identity4 will return me a 4 by 4 identity matrix. That is, A equals np.identity5 will create a NumPy array, identity matrix, okay, whose order is 5 by 5. It's a square matrix obviously, because identity matrix must be a square matrix. Okay. We can also create an array by repeating another array. Okay. For example, let us create this array. Okay. A equals np.array 1, 2, 3. Okay. Observe that, okay, this is a 2-dimensional array. Okay. Look at the difference between this and this carefully. Okay. Did you understand the difference between B and A? B is a vector of 3 elements. Okay. If you look at the shape of B, it will be a vector whose size is 3. Whereas if you look at the shape of A, it is 1, 3. That is, it's a 2-dimensional array having 1 row and 3 columns. Okay, look at the extra pair of square brackets which is missing here. Okay, so A is a 2-dimensional array of having 1 row and 3 columns, whereas B is a vector having 3 elements. Okay. Now, we have A, which is an array, okay, and shape of A is 1, 3. Okay. Now, we want to use this array to create another array, but the array should be repeated multiple times. Okay. So, to create a 3 by 3 array with repeating elements of A, we can use the function repeat. Okay. So np.repeat A. Repeat A how many times? 3 times. With access equal to 0. Okay, access equal to 0 means create rows and then columns. Okay, so this will be repeated 3 times to create a 2-dimensional array. Whereas if you specify access as 1, it will create a vector. Okay, with 1 1 1 comma 2 2 2 comma 3 3 3. So this will be a matrix having 1 row and 3 plus 3 plus 3, that is 3 times repeated. So 9 elements. Okay, if you miss or if you omit access equal to, okay, this argument or this clause of repeat, then this will by default be 1. Okay, let us quickly look at that. You'll understand better. B equal to np dot repeat a 3 times. Okay, if I don't specify access, then B will be this. Okay, and what is the shape of B? It will be a vector having 9 elements. Okay, so this array is repeated 3 times. Okay, that means access by default is 1, that is the third argument is by default 1 if you don't specify. Okay, access. Okay, that is, look at B and C. Okay, C is of the shape 1 comma 3. Okay, whereas if I specify C equals np dot shape repeat a comma 3 comma access equals 0, then C will be, okay, what is A? 1 comma 3. B equals, okay, B equals np dot repeat. B will be a 3 by 3 matrix with this row being repeated 3 times. Okay, so we can use the method repeat, which will repeat this array 3 times to create a 3 by 3 matrix, or if you specify the access as 1, it will create a vector or a 1 by 9. Okay, so if you omit the third argument, then by default access will be equal to 1. Okay, before we conclude for today, we'll look at one last topic. That is, you need to be careful while copying one array to another. Okay, okay, this we already have discussed when we were discussing lists in Python. Okay, the same thing happens in case of NumPy as well. Let us create quickly a NumPy array having these many elements. Okay, if I say B equals to A, what is B? B is the same array as A. Okay, is B different from A? The answer unfortunately is no. B becomes an alias, or B becomes a reference of A. That means if you change a value in B, okay, let me change value, third value to 100, B will be this array now, 1 2 100 4 5. How about A? A will also be 1 2 100 4 5. That means changes that you make to B will be reflected back onto A, because this assignment will not perform deep copy. Okay, it performs shallow copy, and the result of shallow copy is B becomes a reference of A. Okay, how do we prevent this from happening? Okay, you can always create B equals okay. If you do this, then A also changes, because B is a reference of A and not a different array. So how do we prevent this from happening? We already have seen this. copy dot deep copy A to B. Okay, in this case B is a different array that has the same values as A. Unfortunately, okay. And this can also be done using a NumPy method, that is a dot copy. A is an array, NumPy array. A dot copy will perform deep copy of A into B, and B is different array than that has the same values as A. B is no more a reference of A. B is a different array that has the same values as A. Here I am using a method called copy, which is available on ND array, that is A. Okay. Whereas here I am using the Python copy modules deep copy, which will perform a deep copy rather than a shallow copy. Okay. With this, we'll stop for the day, and we'll look at the remaining topics in our next session.